Okay, welcome to lecture 2 of the PCPs. This one we will discuss linearity testing and its application towards constructing constant query exponential size PCPs in today's lecture. So let's begin with a quick recap of what we did last time. So last time in the last lecture we stated the PCP theorem. We stated the PCP theorem in two different languages. One in the language of hardness of approximation max 3 set, and the other in the language of proof checking. And then we showed by the end of the lecture that these two viewpoints are in fact the same viewpoint. So when you're talking about hardness of approximation, the first viewpoint will be the more useful, this one. And then we also saw how it can be used to show hardness of approximating the clique function. But when actually trying to construct PCP theorem, through the PCP theorem, it's a second viewpoint that will be the more useful one. So let's recap. Let's recall the PCP theorem statement, the proof checking viewpoint. So what was the statement? The statement was something like this. That is, there exists a universal constant Q such that for all languages in NP, there exists a C so that L is in PCP 1 minus alpha C log n Q. Q and then alpha and D. That was the statement we had. And what did this statement say? The statement said the following, that is, for every, so you have this language L, and you now needed to check if a given string X is in the language or not. In the classical NP sense, there is a proof that convinces you the membership. If the string was indeed in the language, then there is one proof, short proof that convinces you, which you need to read in its entirety to be sure that that's a valid proof for this. Otherwise, no matter which proof you give me, there is nothing. There's no way you can convince verify. That's the usual notion of NP. And what the PCP theorem is stating is the same that there's a slightly different proof, which is called pi possibly, randomized verifier, which is going to look at this proof only at very few locations, Q. Of course, it comes at a cost, it's going to toss random points. Certain number of random points are. But it looks at the proof. The key thing, the key observation over here is the key difference is V makes only Q queries into the proof. And actually, let's stare at this. I want to say this is quite a remarkable thing. If you're going to read only Q queries into the proof, of course, this Q could be different based on their random points. So each time the random points come out differently, it could be a different set of Q queries. When you write a proof could be wrong. Let's take the proof as a mathematical proof. A proof could be wrong just at one location, one location. So in order to find that the proof is false, you will have to read the proof in its entirety. It might be that every part of the proof is correct except one single line in between. And that one single line could be one single place could be the fatal bug. What I'm claiming over here is that's not the case. If the theorem was in fact false, then no matter how you write the proof, you will most of the time you'll be able to catch the error by just looking at Q locations of the proof. That is, most of the Q locations actually do see an inconsistency. That is, false theorems in the usual language of NP don't have any proof that prove you. That only means that there will be a place that the proof fails. That is, there's one bit in the proof that possibly not correctly given in this one. And so you have to read the proof in its entirety. Whereas what this is stating is you don't have to. This sort of inconsistency, I'm being fairly informal over here. This inconsistency in the PCP, right, is sort of spread across the entire, it's smeared across the entire proof. That is the most choices of the few locations that you pick based on the randomness, you do observe this inconsistency. And that's quite a remarkable thing. It says that you can write this proof in such a way that proof verification becomes extremely trivial. You just need to look at few locations and be convinced that the proof is correct. With high probability, of course. It comes and the cost for this is the randomness invest. The randomized it's a randomized verifier instead of a deterministic verifier. And couple of things. This Q can be made. Observe the thing. Q can be made as small as 3. You can just look at 3 bits of the proof. You can ask why only 3, why can't we make it 2? The first problem set will be released today, and you will see that you can't have 2. Something wrong will happen if you can reduce it further to 2 queries. 3 is the lowest. That's one observation. 2, the randomness needed I said that PCP in the verifier comes at a cost. That's the randomization of the verifier, but that's at most order log n. It's not too large. It's just logarithmically large. Now, question is, why should it even be logarithmically large? We saw that to relate it to the inapproximate thing, it shouldn't be more than logarithmically large because we are going over all possible randomness. Therefore, that when you go over all of them, you need that number to be polynomial. Therefore, the number of randomness could only be logarithmic. You could ask, can it be smaller than logarithmic? You could ask this. And what we will, once again, there will be a problem in your first problem set, which says that if the randomness is strictly smaller than log n, that it's omega log n, then actually any language accepted by such a PCP verifier will be in P rather than in NP. That is, you at least need to invest log n randomness if you want to capture NP. Of course, if NP is equal to P, that's a different story. But assuming NP not equal to P, you at least need to invest log n bits of randomness into the verifier. Okay. And this is something I find extremely surprising, that it makes only Q queries. It's an extremely powerful object. And of course, that comes at this cost. It comes at the cost of the randomization. How does one even write a proof such that you can just look at a few bits and be convinced of the veracity of the proof? The PCP theorem says that every proof can be written that way. What we try to ask is the following game. We want to ask this following question. So there is some proof. I need to check. There is a proof, and I need to check that this proof is correct. So firstly, I need to check that the proof is correct by looking at very few locations of the proof. Now, okay, I need to do this for every possible language in NP, but let's ask, is there any particular property which has this feature? That is, there's some property. I'm going to write strings only satisfying a particular property. Can I check that the string has this property by looking at it at very few locations? So the question which I want to ask is, are there property? Because we will need such, at the very least, we need this to construct the PCP theorem. PCP theorem is static. I'll check any proof. For every language, I will be able to construct proofs with this property. So in particular, let's ask, is there any specific property in which I can just look at a few bits and be convinced that the property is correct or not? So basically the question I want to ask is, are there properties and by properties I just mean sets of strings. It's just a collection of strings such that one can check if a particular string, let's call it f, has the property by probing f at very few locations. Certainly, there are some properties like this. The property of, notice that, strictly speaking, you cannot, if you want to distinguish strings between having this property and not having this property, this is not a doable task because the string might not have the property by just flipping it at one bit. So you want to be able to, what do I mean? You want this tester to distinguish strings strings in the property and strings. I can't say strings not in the property because a string in the property and a string not in the property might differ only at one bit. It's impossible to catch this guy. So you'll say strings, we will relax our goal and say strings far from the property. Far, we have to define what far is. Far is usually in Hamming metric, but so the question is, are there some properties which have this feature? Certainly there is one property. The property in which the string is constant, it has the same location everywhere. That has this property. You just check a few locations, check that they are all equal. If they are equal, you accept. And this should have the property because if something is far from it, you will check it. This test will catch it. But this is not a very interesting property. I want to ask, are there more interesting properties which have local tests? So that will be actually the goal for both this lecture as well as next lecture. We will look at properties which have have local testers, analyze their local testers, and then use these properties actually to show that these are very specific properties, but yet they can be made to, using them you can construct general purpose PCPs. So the first of the property which we talk about is what is called linearity. That's going to be the goal. Most of the discussion for today's lecture. Okay, so what's this one? So we will be looking at strings of length 2 power n. So I'm going to look at a string of length 2 power n. Given such a string, it's easier to look at it and view it as a function rather than as a string. That is, it's a truth table of some function on the Boolean hypercube. So you interpret the string. It's a 2 power n long string, but let's interpret the string as a Boolean function, as a function on the Boolean hypercube in a very natural sense. And we'll say that f is linear. Clearly, we know this. F is linear if.
So we identify 0, 1 with
Huh? Yeah, so I'm going to identify the 0, 1. Here is going to be GF2. The linearity, I'm going to talk about some underlying field. We later on talk about generalization to the other fields, other groups and stuff. But for now, at least for the first 20 minutes or so, let's focus on just the GF2 field and this one. We are given some function. We'll say f is linear if f of x plus y is equal. Is f of x plus f of y for all x, y in 0, 1. This is, of course, a standard notion of linearity, and it should also be clear to you that f is linear if and only if there exists an alpha in 0, 1 to the n, such that f of x is actually equal to summation alpha I xi for all x in 0. This summation is happening over GF2. This summation is happening. This is the only way in which a function. These linear functions, then we call the linear function. In this specific case, we will. If that's the case, we'll say f is the linear function L alpha. It's a linear function given by the string alpha. Notice that there are how many such linear functions are there? There are 2 parallel linear functions, one corresponding to each alpha. And what we want to now do is design the following test. Given a function, the question now is the following thing. Given a function, what do I mean given? That is, I have to has an oracle. Check if f is linear or far from linear.
So, Prahladh, you show that for every linear there is an alpha by some dimension of
Yeah, you just show it
the vector
again.
space of they form a vector space.
They form a vector space, and these are also linear functions, and they are the. Yeah, that's. Okay, so now actually I have we have a very specific problem at hand. I have to define what far from linear means. So what does far from linear? So I need to define this notion. So this is, I'm going to define it by delta f. Delta f is going to be the distance of f and alpha. It's the minimum delta f alpha, which in same sense is minimum over all alpha probability that f of x not equal to L alpha x. So you go, you find it's the closest linear function to this. That's the distance. That's how far it is from being linear. Because if you change so many locations, this becomes a linear function. So this is what we will call delta f. Okay. And so basically, we want to test, we're given a function f as an oracle. We don't get to, we can read whichever, we get charged for querying the function at every location, whichever location we want to charge. So we don't know the function value at all places. If you want to know it at places, you're going to query it. And now we want to check if this given function is a linear function or far from a linear function. I don't care which linear function. I want to check is it close to a linear function or is it far from a linear function? And far is from this notion of, it's a natural notion. It is just the Hamming, it's a normalized Hamming distance. So Blum-Luby and Rubinfeld suggested the following. In 91, suggested the following test. VLR test. For a VLR F So once again, I'm going to throw the course or use this notation. If you don't have explicit access to an input, it's always given as a superscript. That means you only have Oracle access. This means you have Oracle access to the input. And I want to check if f is linear or not. They just said let's use this old definition of linearity, the one in Saffron. Use that definition of linearity, not the second definition. There are these two definitions of linearity. Well, the first definition and see if it's a robust characterization. They basically said try the following. Pick x and y at random. Query f at x, y, and x plus y. They suggested doing the most natural thing, except if f of x plus y not equal to, equal to f of x that's the demon, guys. So let's define epsilon f is the rejection probability of the test. This is the probability if you pick a random xy, f of x plus y not equal to f of x plus f of y. And what I care is that's and what we want to understand is the relationship between epsilon f versus delta. The first statement should be clearly true. If delta f is 0, what does that mean? So the function is linear. Then it should be the case that epsilon f is 0. So this is what's called completeness. If delta f is 0, that is if the function is linear, that is f is linear, then the test accepts, then epsilon f is also 0. In fact, in this case, this is an if and only if. If epsilon f is 0, because that's the definition of linearity. We show that's an alternate definition of linearity. But what we want, so that's completeness. What we want more interested is the following sort of statements. Suppose epsilon f is small. That is, the test rejects with small probability. Does that mean that the function is actually close to linear? That is, if the function test does not reject with too much probability, then does that mean actually the function is actually mostly linear except for a few places, and if you flip that, it actually becomes linear. Okay. And this is exactly what DLR proved. So this lemma is due to DLR. The statement which I'm going to, the proof which I give is due to Coppersmith. We'll show that if epsilon f is not too large, in particular if it's smaller than 2/9, then delta f is less than or equal to 2 times epsilon f. These numbers might seem something like out of the one. We will later see actually these numbers are right. I can't change anything because the proof is more general than the theorem that I wanted to solve. We'll talk about all of this, but let's first prove this. Is the statement here? I'm taking that if the rejection probability is not too large, it's smaller than 2/9, then the function actually is very close to being linear. In fact, it's just twice the rejection probabilities in distance to be linear. And if you haven't seen this proof, this is one of these magical self-correction proofs. It should. So the way the proof will go is we'll actually take the function f, we will self-correct it. Self-correct it is we'll sort of come up with another function phi, which is we come up with phi, which is a self-corrected function. And we'll show that this self-corrected function is actually the corrected function is very close to the given function f. But if the given function passes the test with very high probability, this self-corrected function is actually a linear function. And that will prove the whole result. So what is phi of x? I had to define the phi is this function from 0, 1, n to 0, 1. We define phi of x. What we'll define it to be is, notice that if f was linear, f of x plus y minus f of y, what will this value be? This will be f of x. But as we range over different y, this is going to give different values for it. What we will choose is actually we will choose the, I can say majority over here, but I'm going to say plurality because later on we'll see these groups actually work even when the fields are not. There is range over all f, all the y's, and pick the most popular value. In this case, there are only two values, therefore it's also the majority value. Set p of x to be this most popular value that. So this is sort of the mode that y thinks f of x should be so that the test passes. This is fine. We will prove three statements. Three in this one. One will show. What?
Is this modular to subtraction?
Yeah, because these are 0, 1 values. Yeah, so there are only two possibilities. Yeah, only two possibilities. Yes. So I want to make several sub-claims. The first one of them I want to say is this phi is actually very close, is small. I want to say this guy is small. One delta phi is small. We'll see how small that is in the proof. I want to say this way. Actually, phi is the self-corrected function is not too far from f. And this is actually an easy fact. So let's define a bad set of points x in 0, 1 to n. Be those points such that the number of y's for which f of x is not equal to f of x plus y minus f of y. This is more than half. One thing to pick this one should be there. If X does not belong to bad, then phi of X is equal to f of X. Because if X does not belong to bad, you have at most half the values of Y are differing from, are not giving the quote f of X. Therefore, the most popular value is in fact the majority value. The majority value is specified by f of X. So this is the case. So in particular, this implies that delta Fp, the distance between them, is less than or equal to probability of X in bad. Because if X are not in bad, they are equal. Therefore, the distance between them comes only from possibly things in the bad set. But now I want to say we are more or less done with the proof. What is epsilon f? The rejection probability. This was exactly probability over x, y, f of x plus f of y is not equal to f of x.
Can you repeat what delta f component?
Huh?
What is delta f component?
Oh, it's just the distance between, so these are two strings. These are two power n strings. It's a distance between those. Number of places where they disagree. Okay. The fractional number of places where they disagree. Okay, is this fine? So this I can lower boundless first probability that X is in bad times probability over xy f of x not equal to f of x plus y minus f of y conditioned on x in bad. So this is, what is this? This is greater than or equal to minus a half. And we are done. That's the end of it. This step is not it's a very standard step in most of these fields. A step that is the claim that is the most interesting of the claims is the following claim. Claim 2. So how did we define C? We defined C as the most popular value, or in this case, the majority value. Want to claim actually it's not just the majority value, it's the overwhelming majority. It is for all x probability over y that phi of x is equal to f of x plus y minus f of y is greater than 2/3. Greater than half is just by definition. Half is by definition, at least for Boolean valued functions. But here I want to claim that this fact it's not just half, it's actually 2/3. It's an overwhelming majority. That is the self-corrected function is not just the most popular, in this case, the majority value, but actually the overwhelming majority. Notice it's just a correction, self-correction algorithm. I want to say this is actually correct with overwhelming majority. How does one expect to prove such a statement?
Why is this kind of statement true?
Huh?
What is there? Is there
For what?
for why This kind of thing.
Yeah, so why is this kind of a statement? Why would you believe this kind of statement? It's true. So we see it in the proof of it, but why should such a statement be true? How are we defining phi? Phi is defined by the vote given by several, for every x, we are talking about the vote given by different y's. Now, you want to ask, these two guys are giving y and you're picking the most majority value or the most popular value here. I want to say it's not just the most popular, but it's extremely popular. It's overwhelming majority. Now, one way to look at it, because it's votes coming, you can ask what is the probability that two random votes agree with each other. If they agree with each other with a very high probability, that means the collision probability is very, very high. Now, if the collision probability is very high, then the collision probability is very high. This means that actually it's not going to be a 50-50 coin. It's going to be more like a 3/4, 1/4 coin. And that's basically what's going to happen in the proof. So basically what we will show is choose two random, let's fix a y. So let's look at the proof of this. So and this is standard, this one. So fix any x, fix the x that we want to. And let's pick two random y's and ask what's the probability that both these y's, y1 and y2, give the same vote for this particular x. That is, I'm asking what is the probability that y1, y2, I pick two votes, f of x plus y1 minus f of y1 equals f of x plus y2 minus f of y2. So to say this is the same as probability y1, y2, f of x plus y1 plus f of y2 equals f of x plus y2 plus f of y1. This is the same as, this is certainly at least probability y1, y2, f of x plus y1 plus f of y2 equals f of x plus y1 plus y2 equals f of x. This is at least this one. But the thing to notice out here is this event here, x is a fixed guy, but because y1, y2 are random, the one in red which I circulated just now is an exact copy of the test. Because x plus y1 is a random point, y2 is a random point, so you're picking up two random locations. Even though x is random, x plus y1 is now a completely random location. So this is an instance of the test. Similarly, this is an instance of the test. And these are two instances. The union bound will tell you that this is at least 1 minus 2 epsilon s. Which by our assumption is greater than what, 5/9? 2/9, yeah, 5/9. Yeah, but though you should already realize that is the collision probability is at least 5/9. The collision probability is 5/9. Then the most popular value has to itself be at least 5/9. So let me just state this. What am I stating? That is, like, I'm going to state it in a slightly more general fashion because I'm not. Eventually, we'll see the proof not just works only for Boolean value functions, but for a larger this one. So let's. For each b, let p be the probability over y that f of x plus y minus f of y equals b. This is the vote. This is the amount of times y votes for p. What do we know we know the following: summation over PB is 1 because the total vote as you range over all the V's is 1. And star is just stating that summation PB square is greater than finite. Because what is that's exactly the collision probability. Star is exactly collision probability. Out of this, it should be evident from you that the max. What's the B value which you are choosing? The recall. Phi of x is R max B PB. It's the most popular value. So certainly, hence max PB is at least finite. This is the following that implies max PB summation PB is greater than finite. That implies max PB. Okay, I wanted to prove 2/3, not finite. Finite is smaller than 2/3. You can do one more now. What is PB? So we have. I want to state summation PB square we have is greater than finite. But this I want to state is less than or equal to summation max PB square. Sorry, not summation. Square. So we have, but I'm going to make a slightly stronger statement, but what we have summation PB square is greater than finite. This is at least certainly one of the elements in the summation, one of the elements is PB. So 1 minus max PB is the sum of all the remaining elements. Even that square, that will only be more than, because there are more terms than that than this. So I should have this one inequality. In particular, I should have max PB square. What happens when I expand this guy out? Okay.
How do you do the first inequality?
This is sum over certain quantities, squares of for certain quantities. This is one of those quantities. This is sum of the remaining quantity square. There will be all the cross terms also will appear here. So certainly the true statement. This is a quadratic, solve this quadratic greater than it's quadratic is really like this is it's a quadratic of the form alpha square minus alpha plus 2 by 3 plus 2 by 9 greater than 0. That's alpha minus 2 by 3 into alpha minus 1 by 3 greater than 0. That means alpha should be either larger than 2/3 or smaller than 1/3. We know it's larger than finite, therefore it has to be larger than 2/3.
We wanted 2/3 for some good reason later.
We'll see why 2/3 comes in. Okay, so, yeah. Well, why do I want 2/3? Why did I do all of this? Okay. What have we? Yeah, no, we needed to show. Okay, I should actually possibly done that before this. Why did we do this? We started off with the game plan before. We wanted to show phi is close, the self-corrected function is close to f. And I also want to show the self-corrected function is linear. We haven't yet shown that. We have shown phi is some self-corrected function. Why is phi linear? So that's going to be the third claim. For claim 3, phi is linear. So here I don't get to, I have to show for every x and y, phi of x plus p of y equals p of x plus y. There's no randomness over here. So let's fix some x and y in 0, 1 to the n. Now phi of x is equal to f of x plus c minus f of c, but for less than 1/3 of the z's. That's just because of this overwhelming majority. Is that right? Now phi of x, phi of y. Of course, I can write the same thing. I would also want to write it as f of y plus c minus f of c, but I'm going to write it in a slightly different fashion. I'm going to write it as f of c minus f of z minus y. That's the same. This one. Once again, but for less than 1/3 of the z's. And p of x plus y is equal to p of x plus z minus z minus y, but for less than 1/3 the z's. This is just using the fact that if z is random, a plus z is random. So all of these statements are true. Hence, because 1/3 is less than 1/3 is less than 1/3, you have 3 1/3s over here. These might be different z's for all of them. There certainly exists one z for which all the 3 equations are true. Hence, there exists one z for which all the above 3 are true. For that, and once you have, if it's true for that z, notice that z will show to you that phi of x plus p of y equals phi of x plus y. You just added. For one z, this is one z, all the 3 equations are simultaneously true. Then you do have phi of x plus p of y equals phi of x plus y. That's the reason why I needed 2/3. Notice the key thing here, x and y are not random. It's a fixed x and y. But yet, because I have this fact that phi is an overwhelming majority, there is one z which is going to correlate all of these, put all of these 3 equations simultaneously together, and that z is enough to show that this is linear. And that's where it's a beautiful proof. It's an elementary proof, but it's an amazingly beautiful proof. You can.
How did data
DLR proof was also like this. DLR proof was also like this. This is
the Fourier proof is not.
Fourier proof is not. Fourier proof is good 8 years after BLR, 6 years after BLR. Yeah. But how are we doing with respect to time? Okay, so what I'll do now is, okay, so that's the end of the proof. That's the end of the proof. Hence, P is linear, and that concludes the lemma. Is that clear? Why the lemma is clear? The lemma statement was this following. That if epsilon f is less than 2.9, delta f is less than 2 epsilon f.
So P is the linear function that f is slope.
Yeah, P is the linear function that f is. We have demonstrated a linear function which close to, and that for that I needed epsilon f to be less than 2.9, and I did this.
Do all the proofs have the property that you get your hands on a linear function as well?
So most of these proofs, we will see that in subsequent also, they will have, the Fourier proofs don't have this, they do a self-correction. They will do a self-correction and then show that, yeah, they have this feature. And this is a very nice particular proof. There are two things to learn from this proof. One is the notion of self-correction, and other is to show going from majority to overwhelming majority, the right thing to do. In retrospect, this is obvious. Choose work with collision probability. If you show collision probability is bounded away from half, that will show actually things are overwhelming majority. Now let's make a few observations. On what we did so far. Nothing we did so far used the fact that the function was Boolean, the domain was 0, 1 to the n, nothing. There's nowhere in this proof I have actually used the fact that proof doesn't use domain is 0, 1 to the n or range is 0, 1, 0, 1. It neither uses the fact it's a Boolean function nor that it is a function defined in the Boolean hypercube. In general, I could define this to be, we could do the more general thing, that is G and H could be two arbitrary abelian groups. F is some function from G to H. And we call such a function of homomorphism. If for all xy in G, f of x plus f of y, this plus is happening in the group H, is equal to f of x plus y, where this plus is happening in the group G. By the way, this is a homomorphism even for non-abelian groups in the definition of homomorphism. But the various places in the proofs we have used abelianness. We move things around. So this actually, you give me any function from G to H, and you're asking is it a homomorphism or not? And this proof actually tests that. That's why I call things plurality and all of this, because there's nothing in this proof we actually use the fact that the range is 2. But even if the range were a huge range like size of H, the proof just goes through. It's quite an amazing proof that it works for all of these ones. By the way, the questions asked about what happens for non-abelian, that was resolved. By the way, this proof is from the early 90s. This is 91 or 92. The non-abelian case is fairly recent. The things get complicated. Notice that the proof It's very general, it works for any G and H, but you need abelianness because we've used commutativity of the operation several times over. Okay. And because it's in this generality that 2/9 is the bottleneck, and that so the Coppersmith counterexample. The 2/9 is right. Yeah, so let's look at the case when G is integer mod 3nz for n being a large integer. So it's not integers. So I'm looking at the group G is integers mod 3 and z, where n is a large multiple. N is a large. So n is a large number. N is a large number. So integers mod a large multiple of 3 is what I'm looking at. And let's define this function f from G and H are going to be this group. Let's define this function from the G to G as follows. F of x is 0 if x is congruent to 0 mod 3. If furthermore, so you have one of 3n inputs. If it's congruent to 0 mod 3, you give 0. If it's congruent to 1 mod 3, you give 1. And you give 3n minus 1 if it's congruent to minus 1 mod. Time, but I want to show whether this is an observation, but you have to check it for large enough n. The distance of f from any homomorphism from G to H is actually 2/3. It's very, very far from being a homomorphism. Precisely, the closest homomorphism is the all zeros. Then you can check that out. That's not hard. But given that, let's look at how the test works. I'm splitting the input into 3 parts. This is 0, 1 mod 3, 1 mod 3, minus 1 mod 3, 0 mod 3, 1 mod 3, minus 1. This is when x comes this way, y comes this way. Then I pick x to be 0 mod 3 and y to be, x could be 0 mod 3, y could be 0. I'm looking at the various possibilities for the test. So let's see what happens. Is the square clear to you what I'm trying with the square? So what I want to know, put as a tick or a cross if the corresponding pair passes the test. So if x is 0 mod 3 and y is 0 mod 3, what happens? Does the test pass or fail? It will pass. In fact, if x is 0, it will just pass. Similarly, if y is 0, it will just pass. If x is 1 and y is minus 1, also it will pass. Is that right, actually? Yeah. Therefore, these two will also pass. And the only things that will fail are these. Therefore, del epsilon f for this is 2/9. So the rejection probability is only 2/9, but yet the function is quite far from being homomorphic. And that 2/9, that's the reason why I did some more hard work over it.
Are there other tests for linearity testing that don't extend to mountain?
They don't.
It feels like this tightness is for
No. So
kind of
it's for this kind of a test. But now what we will now do is actually, so the next, okay, so once we have done this, what we're now going to do is, now that we do this, so this is because it's not whether, so there are two ways of asking it. Can I make the test to accept more than homomorphism, more than two group homomorphism? Is it just the test, or is it the analysis was so general? Can I actually take the same test? And what we'll show is the Fourier proof is the fact that if we focus our attention on the group being 0, 1 to the n and 0, 1, we can get a far better analysis.
for the same test.
For the same test. So our question, I push it to the onus of the analysis rather than on the test. So the test, one reason to keep this as the test is there's a more philosophical reason to keep these as test. So this is, where is the picture? This is the definition, the one in orange saffron over there is the definition of linearity. It's a for all definition. Now the question is, if that for all replaces by most, is it still a good definition? So if the question is this a robust definition of linearity in that for a homomorphism? And I don't want to really, of course, for our PCP application, it's fine to give whichever test. But if you just look at homomorphism testing or linearity testing, this is asking, is this definition a robust definition? In that sense, it's better to stick to this object rather than. So this is some place in which linearity testing is said as a property testing. In property testing, we don't care about. Come on. Yeah. So in property testing, we don't care about what the predicate, what the test does, as long as it's a low query test. But what we'll see is actually in several of the tests we care about, we actually care the test is of a particular, the predicate has some nice structure to it. The property testing is completely oblivious to this. They don't care about, they only care about the query complexity, but most of the tests we design here will actually care about this. So the test has to be nice. It should be a characterization of the property, and what we are asking invariably is this a robust characterization of the property. And also the point is, once you do it this way, this has far more connections to math than just the property testing. Math, there are several groups in which you can define some property of a group and say, this is true if only if this for all statement is true. Now, question is, this is called a lot in math, it's called the stability of a group. They'll define an object and say, this the graph has a group has a property if the statement is true for all elements X. The question is, what happens for most elements? Then if you can show that the group is close to being is close in the Hamming metric to a group which has this property, then this is called a stable characterization of it. They use the word stability, we use the word robustness, but it's the same. Okay, so that's observation 2. Observation 3, what I wanted to say is you could ask actually, do you need, so right now X, Y are both independent. From G were independent elements of G. Question is, do you need full randomness, or can you use lesser randomness than? So how much were you been? Okay, so I will shift topic just in about 5 minutes, and then you'll be able to get. So question is, right now we are picking a fully uniform element of X, a fully uniform element Y. Do you really need X and Y to be completely independent? What we show is actually not. Can one use lesser randomness? That's a question that can be asked. And the answer in fact is yes. This was answered by Shrika and Peterson. X is a uniform element. G, Y comes from an epsilon biased set. That suffices actually for the test.
The analysis is similar. You here also you get some linearity based on why children from.
There is multiple analysis for this. In particular, there are two, at least I know two ways of doing this analysis of this. One is look at the graph in which X is, you connect X and Y if they participate in a test. Sorry, you connect X and X plus Y if they participate. Basically, if there's a Y that connects them. And if this graph were an expander, you can show that this one, if it's epsilon bias, it's a Cayley expander. And if it's epsilon bias, it's a Cayley expander, you only need properties of expansion of this graph. You can see the same proof, exactly the same thing will work. The problem set will have, so we will now shortly do a Fourier proof of this for the specific case when G is 0, 1 to the n. In this case, actually, you can get even improved parameters as epsilon bias, so the problem set will have that analysis for the.
What is epsilon bias?
So ignore it. It's some slow randomness space. This will all be defined in the problems. First problem set will have. So we'll continue the linearity test discussion. Okay, let's get to the Fourier proof. Now we will see an alternate alternative analysis via Fourier. And this is for the specific case. When G is 0, 1 to the n and H is 0, 1. In particular, this is GF2 to the n, and this is GF2. The same proof almost verbatim goes for GFP to the n and GFP. It's not verbatim, we have to change the test a little bit, but let's stick to GF2 to the n.
And is that GFP or reason for being prime on this all finite?
No, only if the GFP being prime. So on prime for some bit messy. I think so. No? So let's just focus attention on this. In this case, so what we had the linear functions. And this proof was due to, this proof was discovered, the Fourier proof was discovered due to Prahladh. We see Coppersmith. Harsha. Kiri and Susan. We see the proof is, the list of authors is longer than the proof. This was discovered in 96. So it's a good 5-6 years after the BLR.
That's Kiwi.
Kiwi, yeah. I think he's a South American from Chile. And it's extremely cute proof. The nice thing about this paper is it's one of the papers where there were previous papers where it is a paper which sort of made Fourier analysis the central, the role it plays Fourier, showed how important Fourier analysis is for, at least in I think theoretical computer science. There's Kantalai lineal which introduced Fourier analysis already in the late 80s, but I don't think it took off till basically this paper. This paper was what actually said Fourier is useful. It's a short proof, and so you realize the power that Fourier analysis has over it. So what's Fourier analysis? So let's look at what did we have. We were looking at the list of linear functions. L alpha of x was summation alpha I xi. Here alpha is the function 0 to the n. By the way, how much of you are familiar with the parity functions in Fourier and stuff? If you are, I will just quickly skip to. So what we will talk about are the functions. We will move from 0, 1. It will be convenient to move from the domain will change, the range will change from 0, 1 to plus minus 1. So in particular, any bit b is representing bit b will represent as minus 1 to the power b. It will represent as plus minus 1. Therefore, chi alpha x is just going to be the corresponding linear function. It's going to be minus 1 to the power L alpha x. So this is minus 1 to the power summation alpha n. So these are what's called the parity functions. We'll work with the parity functions. I will notice that there are 2 power n parity functions. So let's look at the space of functions f going from 0, 1 n to the reals. This is a 2 power n dimensional vector space, R vector space, R space. This is a 2 power n dimensional R space. We can equip this with an inner product. Let's equip it with an inner product. And we will be dealing with the space over and over again. We look at functions on the Boolean hypercube, real valued functions on the Boolean hypercube, and this is the inner product we'll be defining. It's almost the usual notion of inner product fg, except that I'm going to normalize it. Expected value of f of x, g of x. The usual is summation f of x, g of x. This is I'm just dividing by 1 over 2 to the n. That's the only difference. Why am I talking about all of this? The key important fact to notice is that chi alpha x's, chi alphas, key of the main observation is that chi alphas form an orthonormal. And the proof of this is quickly see the proof of it. First, I want to say for all alpha, expected value of chi alpha of x as you range over x, I want to say this is 0. As long if alpha is not the all zeros function. That should be just clear because it's otherwise it's equally likely to be plus 1 and minus 1s. For the all zero in alpha is all zeros, this will be just 1 all the time. Which will also mean that for all alpha not equal to beta, expected value of x, chi alpha of x, chi beta of x. Notice this is almost by definition, this is expected value of x, chi alpha plus beta of x. Therefore, this is also 0. If alpha is not equal to beta, alpha plus beta is a non-zero guy. Therefore, this is 0. That's it. And that gives you the whole thing. This tells you that chi alpha, chi beta is 0. Alpha not equal to beta. And it's 1 if alpha equals. And that tells you it's so that gives you it's an orthonormal basis. And they are enough now. They are exactly 2 power n of them. The first space is also 2 power n. Firstly, these are orthonormal because they are the right cardinality, they form a basis. So you have this. There is any function f, therefore hence for any f can be written as f is equal to summation f hat alpha chi alpha, where f hat alpha is exactly f chi alpha. It's this. These are called the Fourier coefficients. So I've just write because this is an orthonormal basis, I'm writing a function in the orthonormal basis. In the basis, I can write any function as a linear combination of the chi alphas. So that's the linear combination. So f hat alpha are real numbers. Real number. And what is this real number? How do you find it out? If you have an orthonormal basis, it's trivial. You just take the inner product with chi alpha. Everything else will vanish except this one particular guy. So f hat alpha will be equal to this. And then these are standard things. Once you have an orthonormal basis, you have this. What you have that the inner inner product f and g is certainly f hat alpha g. Just take the inner product, you open it out, this will turn out to be this. This is what's called, I think, Plancheral's equation, and Plancheral's identity. And with ff is summation alpha f hat alpha square. Parseval's identity. And for basically for Boolean functions, what does this translate to? That is f of x is in plus minus 1. ff will be 1. Therefore, that will be summation of that alpha square. Okay, so now let's go back to the linearity testing. Where is the text? Analyze using Fourier. So what do I mean by analyzing using Fourier? We have these two parameters delta f and epsilon f. We want to write it in terms of the Fourier coefficients. So let's start off. What was delta f? Delta f was recall is the minimum over alpha of delta f. Previously I had written L alpha, but now because I'm working in the plus minus 1, it's chi alpha. What is this? This is minimum over alpha, probability over x, f of x not equal to chi alpha of x. So this is a probability statement. Somehow I want to relate it to the Fourier coefficient. So think of this as the indicator. So I'm going to do some trick which is going to come quite useful. Think of this as the indicator event expectation of x. Because these are Boolean, this is just asking. Let's write it this way. 1 minus probability of x, f of x equals chi alpha of x. So this is min alpha 1 minus, this is expected value of x, because this is a Boolean function, this is just f of x. So the indicator that f of x equals chi alpha. Yes. Now I'm going to write f of x dot chi alpha of x equals 1. Why do I want to write it this way? The reason for writing it this way is going to give me one page is this. This is the same as 1 minus expected value of x. Is that right? This is the indicator event that f of x chi alpha equals 1. This indicator event is 1 exactly when f of x chi alpha is 1, this quantity becomes 1. When f of x chi alpha is only after, because these are all Boolean value function, otherwise it's minus 1, in which case this is 0. So therefore, this is sort of, what am I trying to do here? This step seems like an innocuous step, but it's actually a part of it. This is sort of the, in some sense, is the arithmetization of this step.
Something about the test also changed, right? When you identified the range.
So I identified the range instead of checking that. So basically, it all changed. It's the same thing in the sense that it's plus of the group H. Now the plus of the group H is multiplication. Yeah. So you're checking f of x times f of y equals f of x plus 1. Everything is fine over here. But this opens out to min alpha. The half comes out. So that is a 1 minus expectation x, f of x, chi alpha of x. Right? But what is this? This is the Fourier coefficient f hat alpha. Therefore, this is exactly min alpha 1 minus f hat alpha by 2. In particular, this is 1 minus max over all the alphas. So you write the function in this, write the function in its Fourier basis, find out the Fourier coefficient which is largest, not in magnitude, this is not a, it's not an absolute value, just the largest Fourier coefficient, and that one is telling you which is the closest linear function. And that makes sense because the chi alphas exactly correspond to the parity functions. This is okay. So that's the summary of all of this. And take two more minutes and we finish. Hence, the claim which we have now is this fact, that is delta f is exactly 1 minus max alpha f hat alpha. This is an important step. And you have to, the magic is happening actually in that step. It's called arithmetization. Forget about you later on when you stare at it, you'll realize it's actually why that's a. Now let's do the same thing, whatever we did for epsilon f, for whatever we did for delta f for epsilon f. So what is epsilon f? Epsilon f is probability over xy f of x plus, as Ronald said, it's no longer plus, it's f of x, f of y, f of x plus y not equal to 1. We'll do exactly the same thing as what was done past. This is exactly expected value of xy 1 minus f of x, f of y, of x plus y by 2. So whenever f of x, f of y, f of x plus y equals 1, this contributes 0, which is exactly what I wanted it to be in the probability. Whenever that's equal to minus 1, it contributes 1, which is what I want to contribute. This is the same step as the arithmetization. This step and the corresponding purple step over here are the same thing that's going on. So let's this is so 1, so this half minus half expected value of xy, f of x, f of y, f of x plus y. I'm not going to carry the half on this one, so just let's open up. Let's just look at this expected value of xy, f of x, f of y, f of x plus 1. What do we have? We have Fourier. Just let's open out each one of them in the Fourier basis. Write this as expected value of x, summation alpha, f hat alpha, chi alpha of x, summation beta, f hat beta, chi beta of y, gamma, f hat gamma, chi gamma of x plus 1. I'm just expanding this in its Fourier basis. Just doing that, I just opened it out over here. If you do this, notice the only the expectation over x and y. The only randomness is x, y. Alpha, betas, and gammas are there's no randomness in it. So therefore, I can open out the summation. When you open out the summation, you get summation alpha, beta, gamma, f hat alpha, f hat beta, f hat gamma, chi alpha of x, chi beta of y, chi gamma of x plus y. The expectation can go into the summation. So I'm going to write this and just writing this as summation alpha, beta, gamma, f hat alpha, f hat beta, f hat gamma, expectation xy, chi alpha x, chi beta y, chi gamma x plus 4. Far so good? Now chi gamma x plus y, notice that chi gamma x plus y is exactly chi gamma x times chi gamma y. Therefore, this is the same as summation alpha, beta, gamma. Chi alpha x, chi beta y, chi gamma x, chi gamma y. Now x and y are independent, therefore I can break this up that expectation into a product of expectations. That's just because x, y are here. I'm using the fact that x, y are independent. But now what is this? This chi alpha, but this is just basically the inner product between chi alpha and chi gamma.
Yeah.
What is it?
0 if alpha not equal to gamma.
If alpha is not equal to gamma, this is 0. Similarly, beta not equal to gamma, this is 0. Therefore, the only time this will be 0 if alpha equals beta equals gamma. Therefore, this triple summation will collapse to a single summation. Okay. So what are we at the end of it? We have managed to do that epsilon f is basically half 1 minus summation f hat alpha. But I want to just complete all not we have done nothing so far. All of this is representing the input epsilon f and delta f in the language that we want to. Now comes what BCHKs actually do. They just observe that this is half 1 minus what should I say? This is let's say this is greater than I can pull out the maximum alpha f hat alpha times summation alpha f hat alpha is equal to
That is one.
that's 1 because of Booleanity of f. Therefore, this is half 1 minus max alpha f hat alpha, but this is equal to delta f. So the BCH would be basically the lemma, the soundness analysis due to Bellare, Coppersmith, Harsha, QB, and Sudan basically gives you that for all f, that we always have this, there's nothing to this, we always have delta f is less than or equal to epsilon period. There is no like the 2 by 9 or something that we had for the previous argument no longer holds. For every epsilon, no matter what epsilon f is, the rejection probability is always an upper bound on the distance of the function with the closest to you.
How much did we use in this step?
Huh?
Pulling out max alpha.
How much did we lose the step? So, given the rate parameters, what's the static? So let's look at the case when the function is f is a random function. If f is a random function, essentially the test passes with probability half. There you don't expect to get a closeness to linearity, and this will give you exactly every function is half close to linearity.
But that makes sense, right? For a random function, all the Fourier coefficients will be roughly the same.
Yes.
So this is not very lossy. Pulling out max.
Yeah. So there have been work. There's been work by Kali, Kaufman, Simon Litson. What they show is that the second order term, there's a delta square that comes into the picture rather than the first order term. They show you can get a slight marginal improvement over this, but then you'll have to use Booleanity in an even more crucial fashion. Here we are using Booleanity in just one cell in the Parseval. That's the only place where we are using it. So that's important. This is where we are using Booleanity of. Here using Booleanity of. Yeah, but other than that, I don't think this is so it's not correct in the one when epsilon f is 1 minus epsilon. It's like 1 minus something, it's not correct, but at the half plus this one, I think this is close to being correct.
So the closer f gets to a linear function, the more lossy that.
The more lossy that is. So when these numbers are like half plus something, this is the right analysis. And the numbers are closer to 1, this is not. Okay. Okay, already short 15 minutes, but we started list. So let's break now and meet at 15 minutes, 11:30. Yeah, the entire BCHKS analysis is exactly just those 3 lines. And okay, that's a bit of a not giving them new credit, it is this limitations. That's the going from this probability statement to this statement. That's the actually that should be what you give them credit. But this is it's actually in retrospect, both Boolean functions, it seems something new, but if you look at it on ESP, this is the most natural thing to do. That is, this is the same thing as let's pause now and Okay. Let's
Sorry, I forgot to explain.
okay, so let's resume on the second part of today's lecture where we will use. So, what did we do so far in the first part of the lecture? The first part was motivated by the fact is there any property that in which you can test the property by just looking at a few bits? Not read the entire string to check if a particular string has a property, you check it. And one such property that we were able to show is the question of is a given function a linear function. A function is linear if this is how we define a Boolean function to be linear. Exact thing in Saffron. And then we showed that there's a natural test for it, which is basically asking if that definition, if that characterization of linear function is a robust characteristic. Suppose it was not true for all xy, it was true for most xy. Does that mean something for the function? And basically the analysis we showed that is if the test passes with probability 99%, that means the function is there is a linear function which agrees with this function 99% of the time. That's what this final statement shows. So we did show that there's you can check that a string, an exponentially long string, 2n long string, is linear or not by just querying it at 3 locations. This was a necessary feature which we wanted to construct PCPs. We wanted to be able to check that some string had a property by looking at it at very few locations. He asked, is there any such property? One such property was linearity, and that's what we gave 2 proofs for it. One proof due to Coppersmith, and another which was actually more general than what we wanted. It actually showed homomorphism testing. And then the second proof due to Bellari, Coppersmith, Prahladh, Kivi, and Sudan, which was for the specific case when the groups were 0, 1 to the n, and when the domain was 0, 1 to the n, and the range was 0, 1. Okay. So now what we'll ask is, now given this, okay, this is a specific property, can we actually construct a PCP out of this? So, and amazingly, we can.
PCP for everything in
For
something and something.
So what we will show is actually we will construct a PCP for every we won't be able to. So let me state what we're going to show in the part 2 is the following. The key thing about this was the fact that it was constant query. So we will construct a constant query. The PCPs, but unlike the usual PCPs, which are polynomial sized proofs, this will be an exponential sized PCP. But we will not construct it for just linear problem. We'll actually construct it for an NP complete problem. Particularly, we'll do it for circuit set. We will use what we did in the first lecture to construct a constant query exponential size PCP for circuit set. So this is the amazing thing about this PCP is constant query. The verifier is going to be reading the proof only at a constant number of locations. It's not going to be the PCP theorem because the number of randomness, or rather the length of the proof will be exponentially longer than the original NP proof. The NP proof is, say, if it's n square long, this will be exponentially longer than it. The PCP theorem guaranteed it's only polynomially longer. This doesn't prove the PCP theorem, but it gets you the constant query aspect of the PCP theorem. So Rn will be, in fact, the Rn which you will get will not be order log n, it will be order n square. That's the reason why the proof will be this one. It will be a verifier, which makes verifier will make, I think, 14 queries or 16 queries, but the randomness it process will be order n square rather than order log n.
For example, in zero knowledge field, it's supposed to give a zero knowledge protocol for one particular NP complete language like free and that is not true for PCPs.
That's true for PCPs also, no? Because you just read the very.
But in the reduction again, it has to be present.
No. Why?
Verify can run the reduction.
The verifier can run the reduction.
Okay.
Yeah, so it's exactly the same situation. Once you give it for circuit set, it gets for every problem in NP. Every problem in NP, you get it. Okay. So what's the thing? This, by the way, this construction is due to the construction is there. In fact, it is an essential ingredient in the original proof of the PCP theory. So this construction is actually one of the chief contributions of the final of the PCP papers. It's a paper due to Arora, Lund, Motwani, Sudan, and Segel. So they use the DLR test to actually construct this. So what is it that we want to do? So let's start off with the problem. We are given circuit set. What is it that we are given? We are given so the input. This is circuit C. And the goal is to check if there exists a Z such that C of Z equals 1. That is, the circuit is satisfied. That is, there is a assignment to the input gates of the circuit such that the circuit evaluates to true. Now, for simplicity, we are going to make several assumptions about the circuit, which are all without loss of generality. We will assume that the circuit has, so let's make the following assumptions. We'll assume that the circuit has only and NOT gates. There are no other types of gates in this one. This is without loss of generality. We can assume that everything or can be done, or you can do or using be more than with and not. And furthermore, we'll assume that AND gates are of arity 2. But this is for larger arity, you break it down into multiple AND gates. So the AND gates of arity 2. That's the so that's the assumption we'll make. So we have this object. Then the number of gates. This is including the input gates, the output gate, and internal gates. Usually N is used to refer to the number of input gates, but I'm going to say N refers to the total number of all these gates. This is what is going to, I'm going to call N. Convenient for me to know this. And what are we interested in? Interested is that there exists a Z in 0, 1 to N. Of course, such that C of Z equals 1. This is what I want to do. But let me not write it to C. So basically, I want to say C now is now going to represent to me not just the value to the input gates, it's going to represent the value at every single gate. It's the so does there exist a Z? This is a setting to all gates. That respects the functionality of the gates. Okay,
And the top gate is 1.
so then I have included the gate output as a gate. So that was taken care of by that. One taken care of. One. So how am I going to now? It will be easier for us to write this in terms of ands and nots. It's better write it in terms of polynomials. So I'm going to write, so we will have a polynomial. So this condition that respects the functionality of all gates We will check this by having, the way we will do this is by having a polynomial constraint corresponding to every gate. For every gate, we'll have a polynomial constraint. A constraint Pi. Pi is once again from 0, 1, n to 0, 1. We think of it as a polynomial. So it's more of, it's the n variant, so it's like f2n to f2. And let's just see what is Pi of z. So if this were if I is an output gate, then all I want to check is this is Zi minus 1. I want to check something. Let's make it. If the circuit is no, let's keep it. Let's keep it one. One. What check? So basically, the polynomial Pi, I want to check that every gate has a constraint, and you want to check is there a common z such that for all the polynomials you have Pi of z equals 0. So the output is going for the output gate. That's the constraint you need to check. Zi minus 1 is 0. If I is an NOT gate, whose input is the output of gate J, then what are you going to check? You're going to check Zi minus 1 minus Zj. That constraint should be 1. If I is an AND gate, with inputs from gate J and K, what are you going to check? You're going to check Zi minus Zj Zk is 0. And finally, if I is input gate, I don't need to check anything, therefore that's constraint is just the 0 constraint. Basically, what we now need to check. So PIZ is sort of encoding within it the entire circuit. What we want to check is there exists a Z in 0, 1 to the n. Let's call it f2 to the n. Such that for all I, we have, for all I gates, Pi of Z is 0. This is what we need to check. Of course, one way to give it is give me the proof, give me the entire string Z, and then you go and check this. But I want to do this. So this is the NP proof, and this is what the predicates are. The predicate is doing, the classical NP proof. What we will now do is we will write this in a slightly different form, so that the verifier, instead of making these n checks, it will just make, we will write this proof in a much longer format, so that the verifier will query that object only in few locations, say some 10 locations, and be convinced that all these conditions are satisfied. That is, if the string, if there was in fact a Z that satisfied it, then there is one proof which will convince it always. If there is no Z, no matter what you write here, half the large fraction of the time, even though you're reading only like 14 bits, you will be able to find an inconsistency in the entire proof. Okay, our goal is to write Z in a PCP format that allows for local check. That's sorry. Okay. And by the way, PCP theorem doesn't tell you that the PCP proof should be some version of the NP proof. It just says there is some this one. But almost always all construction, the PCP proof will be an encoding of, it will actually take the NP proof and apply some code to it and get this longer object, and that will be the NP proof. The PCP theorem doesn't state it, but all proofs that I know of the PCP theorem are basically there will be an encoding going from valid proofs, valid NP proofs to valid PCP proofs. Using an error typing code, and further we'll see the various things. We will need the code to be a good error correction. It won't be just one code, there will be several codes. Because sometimes we'll have to use a couple of codes to do this. The codes not only have to be error correcting, as we'll see. So the code will have to be also locally testable. That is, you need to check that the given string there is a valid code word by looking at it at a very few locations. This is a necessary feature of it. So we'll want it. And what I want to first say is, so that's what we want to do. So we will encode the PCP. The PCP is going to be some encoding of Z using an error correcting code which is locally testable. Now, what is a good locally testable code? We haven't this one. So what I want to say is actually from what we saw in the previous part, in part 1, we want to say there is a code which is the Hadamard code, or also called the Walsh-Hadamard code, which is actually a good locally testable code. It doesn't have good rate, but it is a locally testable code. And the code we will use is the what's called the Hadamard code, or sometimes they also referred to as Walsh-Hadamard. WH. Code. And what is this code? The code is very natural. The given X, it's a code. Walsh-Hadamard encoding takes a k-bit string and encodes it by a 2 to the k-bit string. And natural, what does the code do? It takes a Z and outputs L alpha of Z for all alphas in F2. So it's it gives the evaluation of every possible linear function at this point. Notice this is almost a linear function. The linear function, so this is not what I call a linear. So this code, I can also have viewed it as Z specifying the coefficients of a linear function, and this is the truth table of that linear function at every point alpha. But that was the viewpoint I took in the first half of this lecture. But I'm going to flip it around and I'm going to say the same, because this was symmetric in alpha and Z. I'm going to view this as not the truth table of the linear function specified by Z, but instead as the evaluation of every linear function at the point Z. In the case of linear functions, these are the same. This is no longer the same when you go to quadratic or cubic functions. These two will become very different objects. But for now, so the viewpoint taken is different. Notice, and I want to make this point, it's a different viewpoint from the previous part. They are the same code. This is exactly the code. This is the truth table of the linear function corresponding. This is exactly the truth table of the linear function LZ. But I will view it not as a truth table corresponding to LZ, but as the evaluation of every linear function at the points. It's identical. There's nothing different. It will just be convenient to do this. So why am I doing this? The point is, we want to eventually, so what we are going to give in the proof is we are going to, instead of asking the proof to give Z, we'll ask the prover to give WH of Z, Hadamard encoding of Z. Why? Because this is an encoding. I can check if somebody gives me a long string of this form that is a valid code word or far from it using the previous test. I can make 3 queries and test it. So as long as, so if I have, so you expect us the prover to give me this long table, we can check with 3 queries that it actually is a linear code or not. Now, once we have that, let's for simplicity assume that we didn't have the AND constraint here. Or else the AND constraint was, it was not a quadratic equation, but it was actually a linear equation. Then suppose I want to check if PIZ is true for all i's. What would you do? You could query each of the PIZs is a linear function. Okay, there are some affine constants here, but those are, you can add them. You can query just the linear part of it and then add the constant yourself to query later. So let's assume all the PIZs are linear functions. You can just go ahead and query this Walsh-Hadamard at those linear places and get those values. But that's not good enough because the prover could just go and mess up. You want to check that all these linear functions are satisfied. There are n linear functions that you care for, and you want to satisfy that they are satisfied. What you can now do is just take a random linear combination of these linear functions and query the proof at that location. So what I want to say is the following. We'll do the following. So let's assume that Pi has only linear constraints. This will not work because Pi has a quadratic constraint corresponding to the not function and the AND function. But for let's just work with this. So then this is the following proof I want to give. So the proof Pi will be, I'm going to expect as the Walsh-Hadamard encoding of Z. So this is what I expect the prover to give me. And then the verifier's test will be the following. So this is the prover gives me, what does he give me? He gives me some function f(0,1) to the n to 0,1, which purportedly is f is actually L of Z. It is this one. It is the linear function corresponding to L of Z, but it's unclear whether the prover is actually, he could have given me something or the other there. So the verifier's test is the following natural test. Pick x, y at random. You first do the linearity test. It has several parts to it. One. Linearity test. You pick, which is just pick x, y at random from f to the n. Where you f at x, y, x plus y. Reject if f of x plus y not equal to f of x plus x. So at the end of this, you know that if this test, at this point the test is accepted, you know that the f function is actually close to a linear function. It's the Walsh-Hadamard, it's close to the Walsh-Hadamard encoding of some z. Now you need to check that z is actually a satisfying assignment to the circuit. So then you do this, you pick, now you do the circuit consistency test. Pick field constants. Field constants A1, A2, AN uniformly at random from 0, 1, n. And let's construct the function P of Z, which is summation AI PI of Z. It's some random linear combination of all the functions. This, by definition, is some L alpha of Z plus some B. It's some linear. If assuming P was a linear function, this is exactly something of this form. So then you just query F at pick. You want to query. So you now know. So you now know that. You now know that the Walsh-Hadamard code is actually what the code which you have is actually close to a linear function. So you could, in principle, just query it at a location. Can you query it at the location alpha?
You can, because they are in the random.
Huh?
What is alpha?
Alpha distributed.
Huh?
What is alpha?
Alpha. So AIPIC is a linear function. And that linear function, I'm writing it explicitly, that's the linear function plus B. So it will be a random linear function. Where
One echelon level.
huh?
Something like later one echelon.
No, you don't need it just so what
No, that's not correct. I mean, it's not a random. It's a random linear function in the subspace bandwidth.
it's a subspace bandwidth. So it's not a random. You know that if you pick a random point in the Walsh-Hadamard, F you know at this point of time is close to a Walsh-Hadamard. So at a random location, it is close to L the correct encoding, not at an arbitrary location. And this need not be a random location.
Even if the goal right level,
You don't. It's much simpler than that. You want to query a linear function at a, you know, a linear function is good at random. You want
E and T's or alpha.
yeah. Just pick. So just let's pick a random. Pick a random R and 0, 1 to the n. Query F at R and R plus alpha. Because you want to query it at alpha, you query it at R and R plus alpha and accept. Writing all of reject. Reject if f of R plus alpha minus f of R plus B is not equal to 0.
So here they only say taking the consistency of the not gates and property.
I'm assuming magically that the gates are all linear. So this is not this thing we have to fix it. The rest of the lecture is going to be go on how I go ahead and fix modify this to even handle quadratic space. But I want to claim at this point that's the whole point. If the function, in particular, if the function was, if the test was just suppose your circuit C had only NOT and XOR gates. Then this is, of course, in that case, it's easy to check that there is a Z that satisfies it because that's just a linearity check. You're just checking something in the map vector space. But I want to say, even in that case, this is a non-trivial statement. The fact that there's such a Z is actually unclear in what sense it's non-trivial. I want to say, in the magical case, when all the constraints are linear, this one does that. We'll have to analyze this.
It's not trivial in the sense that if you're not just interested in checking satisfiability of the linear system, but you're interested in satisfiability by this.
Yeah, so you have to make that precise. I have not made that precise yet. So yeah, so that's why you can. So that this particular input set, if this test passes, what do you know? If this test passes, suppose P was a linear circuit, there were no AND gates or there were no quadratic systems. If this passes, then you know with high probability, whatever you see in this Walsh-Hadamard encoding is actually close. There is a Z. Whatever you see in F is actually. So let me state this correctly. We will not prove this, but because we are going to prove the actual statement. So what the main soundness claim will be the following. Assuming P has no quadratic constraints. This is a big issue and we need to fix this. But for now, let's assume this. I want to say that if verifier, if probability verifier, when it accesses the function f, is accepts is greater than 1 minus delta, suppose this were the case, then I want to claim what Mrinal was trying to say, then there exists a z in 0, 1, n such that f is delta close. Two things happens. One is f is delta close to the Walsh-Hadamard encoding of z. That is, f is actually LZ of f is that, and two, z is a satisfying assignment to the subject. And this is why it's non-trivial, because it's letting you check that this huge object out there is a satisfying assignment without reading that this object. We haven't proved this, but we will prove the more general case when it's quadratic, so I will not prove this. But then once you see that proof, you'll see why this works out.
That's not the BLR testing itself you get real-time. So shouldn't it clearly? But that's not the BLR
The
testing.
BLR testing will give you this. But I want to say that the BLR testing will tell you that
Yeah,
F is
to some Z.
some Z. Now, furthermore, you want to say that Z is actually a satisfying assignment. And that should be just trivial out of this, because there is some, you have now committed to a linear function. There's some probability that the bits you read are not going to be the linear function. That's some 2 delta.
Okay, but then the distance is half.
Distance is half, therefore you will, that's it. That's basically the whole proof of this statement. Yeah, so you're using both the fact, you're using 2 facts about the code. The Walsh-Hadamard code has distance half, it's a good code, and the fact that it's locally custom. Both these properties are being used. Okay.
So I can, where did you use the distance?
If it was the encoding of so different Z to then it would be
The first thing will tell us that it's a valid encoding,
Yeah,
but may not be the same as the satisfying.
may not be the same as satisfying. So if it were not as satisfying, then at least half the places it failed, that half of the distance will. Yeah. Okay. So, but we need to handle quadratic constraints. Yes. So far what did we give? The encoding, the Z, instead of Z, we also gave L of Z, which is the Walsh-Hadamard encoding of Z. We gave the evaluation of every linear function at this point. One. What we'll do is, okay, given this, you want to, question is the PIs. If I did this test over here, if I did this sort of a thing here, I won't just get an L alpha Z, I'll also get a quadratic part. I'll get a quadratic thing. So what we'll do is we'll have another table which will give you the evaluation of every quadratic function also on the input. And then let's see how to test it later. So let's. So I'm going to give quadratic encoding, quadratic WH encoding. I have no name for it. Quadratic encoding. Which is basically, I'm going to map the Fourier one A string 0 1 to the power square string, which is what am I going to do? I'm going to map Z you give me any matrix M in 0 1 to the K square, and it will map, I will give you Z transpose M. Basically, I'm going to give you this That's right. What is quad Z? So I'm going to map Z to a string which I call quad Z. Just like previously I mapped L to LZ. And what is quad Z? Quad Z itself is a 2 power k square long string. So I will view it as a function. And what function is it? It's a function like this. It's a function from 0, 1 k square to 0, 1. So the 0, 1 k square, every element of the input, I can view it as a matrix. What is it going to output? It's for every element m, it's going to output summation mij zi zj. It's this function. Quad Z is this function. Makes sense? So what am I giving you? I'm viewing the input as this is how I'm supposed to view the input. I'm giving you possibly every evaluation of every possible quadratic function on the input. That's what quad Z is. There's few observations. The function quad Z itself is a linear function. Because let's make a couple of observations. Quad Z is linear. That is quad Z of m plus quad Z of n. If I give it two matrices, by just the way I defined it, this is quad Z of m plus n. Therefore, I can check that quad Z is in fact a linear function by just doing linearity test on it. But that's not sufficient for us. We need to check that not only is it a linear function, it's the linear function given by the Zi Zj transpose. So so the f from 0, 1 k square to 0, 1 is linear if there exists a matrix B such that f of any matrix M is basically the inner product of M with B. This is just and this inner product is usually just the element wise. That's just that product. That's just by we will refer to linearity. But this is not sufficient. We want if f, but if f is quad Z, then this matrix is actually, you can check, it's actually ZZ transpose. That's the matrix that will give you that. It will be the outer product of Z with itself. Okay. So what we need to check, so now the new proof will be the following. The now new proof will not only give the Walsh-Hadamard encoding of Z, we'll also give the quadratic encoding of Z. And we'll have to check first the Walsh-Hadamard encoding is correct, then the quadratic encoding is correct, and then we have to check that the Walsh-Hadamard encoding and the quadratic encoding are referring to the same. There are several things we have to do. The proof will have just now two parts. It will have the Walsh-Hadamard encoding and the quadratic encoding. These will be, the proof is going to be given by, so this is a 2 power n long string, and then there's a 2 power n square long string, which is the quadratic encoding. I give you this long, exponentially long object. You can run linearity test on the first object, check that that's linear. You run linearity test on the second object, test that that is linear. So you're fine. But now furthermore, you want to check that. So now let's assume that both these are actually honest to God linear functions. There's no. You want to check that the linear function given by the second guy, the matrix B is actually the matrix ZZ transpose, where Z is the guy corresponding to the first, this one. So we have to do this quadratic consistency test up between the Walsh-Hadamard encoding and the quadratic encoding that they are referring to the same Z. Okay, so we have to design this one extra test. So the test won't be just these two. So previously there will be a linearity part, there will be a circuit consistency part. But in between, you'll have to check that the quadratic encoding and the Walsh-Hadamard encoding are both referring to the quadratic encoding is referring to a matrix B is just given by the linearity test. But that matrix B is actually ZZ transpose, where that Z is coming from the Z coming from the Walsh-Hadamard encoding. We need to do this thing. So the question of how do we design that test? So we need to design question. We need to design a test. So we are given two functions, given functions f, which is going from 0, 1, n, 0, 1, and then capital F, which is going from 0, 1, n square to 0, 1. We will check that firstly S is linear, capital F is linear. So that means that F, so once you have left linear, so you can assume F is LZ. And you can assume F, capital F is LB. It's linear corresponding to this. So these two, let's assume we can get. Need to check B is actually ZZ transpose, but you don't get to read all of Z. You don't get to read B, but you just get to query F and capital F at a few locations. Based on that, you need to be able to do this. Okay. Yeah. So we will basically use we're going to use Prahlad's test over here. Okay, that's exactly what we're going to do. So what am I going to do? I need to check B is ZZ transpose. I don't get access to B. I don't get access to Z. I only get access to B on an inner product of B with a random matrix, and inner product of Z with a random system. But then there's a natural way to look at it. Like let's just pick. The suggestion is the following. Pick xy at random from 0, 1 to the n, and let's look at x transpose by. This should be equal to x transpose z, z transpose y. We need to check. Let's check this. I want to claim these is the x transpose by. This is the same as B xy transpose, and this is the same as xz yz. This is the same as xy transpose B. This is xz yz. This is the query. This is f of B. Sorry, this is f of xy transpose. This is the f of x. This is f of y. So I can make this check. So we try to, this is the check we'll suggest. We'll pick xy at random, do this test, and ask if we can. And if this test passes with high enough probability, does that mean anything? By the way, once again, you should do this. The query, we know F and capital F are random, we know that they're only close to linear response. So we have to query them only at random points. We can't be querying them at this is a random point. This is good enough. This is a random point. This is not a random point. XY transpose is always a rank 1 matrix. It's not a random matrix. So you do the same thing. You sort of translate it by a random matrix, query it at this way. So the quadratic correlation test is exactly the following test. Quadratic correlation test. Its inputs are capital F and capital F. You pick XY at random from 0, 1, n. So not the F is from 0, 1, n. Capital F is 0, 1, n square. 0, 1. Pick XY at random. Pick a random matrix n from 0, 1, n square. So, rather query F at XY transpose plus n and small f at x and y, and accept f of XY transpose plus n minus f of n equals f of x into f of y. We have to analyze this test, but I want to claim a test that we can do. The whole point of this test is we only have access to F at a random location, capital F at a random location, small f at a random location. So the B's and Z's are given to us implicitly, and we need to check that that B satisfies B is equal to ZZ transpose. The claim is this is a candidate test. Is the test okay? The definition of the test.
Why are we picking n?
Because the point is all the points is if F and capital F were linear functions, we could have just whenever we query them, if we know that they are always going to give the linear function, we can have just queried at F of XY transpose. But the point is you only know it's close to being linear. So it's correct at a random point, not at correct at a random matrix, not at all the matrices. So all the points you query should the marginal at any point you query should have the uniform distribution. So XY transpose it's the same reason. It's the same reason exactly. We did this over here too. We didn't query it at alpha because alpha does not have the uniform distribution. We queried it R plus alpha because the marginal is the uniform distribution. So every point, the point you query should have the uniform distribution. And it's exactly the same reason I'm going to be doing it here. XY transpose is not a random matrix, it's a rank 1 matrix. Therefore, you make it into a random matrix by adding an n to it. You query it at these two locations. Do this. Because it's the linear function, you can do this global decoding. That's quadratic correlation test. And I want to say that this has the following features. Completeness: if F is LZ and capital F is LZZ transpose, then certainly the test accepts with probability 1. then probability, the quadratic correlation test. Yeah, F subs is equal to. So the more interesting thing is the following. Suppose F is delta close to LZ. This we can guarantee because of the, if you run the linearity testing, you can guarantee F is close to LZ. You don't have to do this. And F is delta close to LB. And B is not equal to ZZ transpose. For this, you need delta to be small enough so that there are not multiple, so that Z and B are uniquely fixed by this. This one. So this is delta less than half. No, 1/4. Then I want that the probability of the quadratic correlation test FF subs upper bound. So I want to put an upper bound on this. Okay. So there are several bad events that can happen. Let's find out what are the bad events that can happen. One is f of x does not happen to be equal to LZ of x. That is, you happen to query a point x which happened to be this one, but this happens with what's the probability this happens? Delta. So this is at most bounded by delta. The same thing is true for f of y not equal to LZ of y in delta. Similarly, f of n is not equal to LB of n. Sorry.
N plus x by transpose.
Transpose plus n not equal to LB. Because these are all, this is where I use the fact that they are all random points, that they are the marginal at every one of them is uniform. Now the other case is the fact that you actually, the points now in the fifth case, I'm going to assume that you actually read off the linear functions correctly. What is the probability that despite that, so what am I asking now? What's the probability that XY transpose B, that's how I wrote this question. Yeah. Happens to be equal to XZ times YZ. What's the probability that this happens?
This is the same probability you get in Prahlad's test.
This is exactly no, what is it half? It's 1/4, no? What's the probability that this will happen?
You get a linear constant for B.
You
get a linear constant for B.
Yeah, but it's not so basically what's happening over here, this is the same thing as asking what is that is, I'm asking what the probability of this event. What's the probability? Then I pick XY at random. This is exactly the probability X transpose B minus ZZ transpose Y is 0. These two statements are exactly the same statement. So I want to claim this is So let's just
Suppose the condition on every p variable except one of x and y, and it has only one possibility.
yeah.
So it's half.
No. So that free variable should be 0 in both x, non-zero in both the x location. So what is this? So I want to say that let's define C to be the matrix B. This is exactly the free word to C transpose. Now, even if one location of C is non-zero, I want to say this will happen with probability at least 1/4. It's not 1/2, but it's 1/4. So suppose Cij is not equal to 0. If C was fully 0, this is always going to be 0. It's a probability 1 even. If Cij is non-zero, I want to claim probability over x and y. X transpose Cy is equal to 0. This is the same as probability xy xij plus summation I prime not equal to I.
That is x and y j.
Sorry, that's itself. J prime not equal to j. Cij xi yj equals 0. This is what we want to say.
There will be also some where I prime equals to I, but j prime not equal to.
Yeah, this is I mean or. So that's right. Just taken out that one guy and the rest. Either I prime not equal to I or j prime not equal to j. So all the remaining guy. So condition in all of this. Can I do that condition? I cannot do it this way.
And you said every other bit keep xi and yj like you get a quadratic function.
Yeah.
But here
Here you can condition.
the probability half when you set yj, this will remain a linear function in this and that has conservation. Otherwise, we
Yeah, so okay. I'm going to say it this way. Possibly this is what we want to do. I want to say with probability half probability half over choice of y. Cy is a non-zero vector. And then with further probability over x, x transpose Cy is non-zero. Conditioned on that, with probability half over x transpose Cy is not equal to 0. And hence we get the probability. So all I want to claim is this one is the probability of this can be just 1/4 plus 4 delta. That can be the maximum. Otherwise, sorry, 3/4 plus. 3/4 plus. Three-fourths plus 4 delta. Yeah. Okay, so now we are in good shape. Now let's the PCP verifier.
How is saying like probability half C y is non-zero?
Huh?
The element puts.
Which one?
Okay.
Yeah. There's a non-zero, Cy is non-zero, therefore there will be a. Yeah. The input is a circuit C. To show that there exists a Z such that CZ equals 1. We expect as proofs F going from 0, 1, N to 0, 1. In the honest case, F is actually, it takes the actual NP proof and writes the linear encoding of that. And also capital F capital F is quad C. Okay. And now the verifier F and F and input C. It's going to do the following. It's going to run the linearity test on F and F. That is basically it's going to pick XY at random from 0, 1, n and check f of x, that f of y equals f of x plus y and reject that, right? And check this pick n random from 0, 1, n square and check if f of m plus f of n equals f of m plus n. That's the linear part. At the end of this, it notes that the tables f and capital F are linear functions. Then it's then going to run the quadratic correlation test. And actually, it could use the same XY because they're just going to do union bounds on it. I separate XY, but it's the same thing. You could say pick an XY at random from 0, 1, n, the n at random from 0, 1, n squared, and accept if f of xy transpose plus n minus f of n equals f of x. And then find the circuit consistency test. So we did that before, now you can do exactly what we wanted to do. Pick A1 to AN and random from 0, 1 to n. So that's a random linear combination of AI, the PICs. So this looks like what? You know that this is going to look like some constraint of the form. Some matrix B times ZZ transpose plus some alpha times Z plus a B. That's a quadratic constraint. It looks like a quadratic part, a purely quadratic part, a linear part, and a constant. So query F at alpha and alpha plus R, capital F at P and B plus N. Here R is a random 0, 1, N is a random n square, accept if f of b plus n minus f of n plus f of alpha plus r minus f of r plus b equals not stable.
So yeah, if instead of taking a random linear combination of the equations, but then it simply take a equation at random, because after that you're randomizing one another.
So if you pick an equation at random, could be just that one equation is violated. Therefore, the probability that you will catch it is 1 by n. Whereas here, the probability that you catch it is half. If you take a random linear combination That's why that 1 by n is becoming more.
Actually, odd number of terms.
Yeah, it boosts the 1 by n to 1 by half. It makes this huge jump from inverse polynomial gap. Notice the whole PCP theorem, that's the game. The PCP theorem, if you wanted an inverse polynomial gap, that's trivial. That's what the NP, it says all but one constraint is satisfied, you have an inverse polynomial. You want to push it to a half gap. And this random linear the Hadamard encoding has this. If there's an error one place, it will be error half the places it will disagree. That's what is happening over there. And you're using that crucially in this linear combination. So this step is where the gap is amplifying from 1 by n to half. This is the crucial point here. The rest is all set up so that I can apply this. So the analysis should be almost trivial given what we have. Certainly, this should be true. Completeness. If z is equal, if cz equals 1, then f equals lz and f equals quad z will satisfy that probability with the verifier on ff. C accepts is equal to. This should be clear from the previous letter. Soundness will be more interesting.
So it's enough to normal some error probability for each of the steps and
Yeah. So we're going to be quite later on we might want to do more cleverer analysis. Right now we will just get this. So all I'm going to say is this is what we prove. We prove there exists a delta naught in 0, 1. In fact, this delta naught I think will be 1 over 20. Such that for all delta less than or equal to delta naught. If the probability that verifier FF accepts is larger than 1 minus delta, then I want to claim it must be the case that there is a z that satisfies the test, that is an accepting thing. F is delta close to L of z, and capital F is delta close to this one. So I want to say, then that implies there exists a C. Notice that in this case, all I want to show is there exists a CZ equals 1. That will prove the soundness statement. But I will prove that this soundness statement for the PCP verifier, that's all I need. In this case, I have 1. But therefore, there exists a V such that F is delta close to L of Z and capital F is delta close to quad Z. Almost the proof should be, there's nothing, the proof should be evident from now. So let's write down the various possible bad events again. F is delta far from being linear. That could be the case. That f is already delta far from being a linear function. In which case, you know that you will what's going to be you will reject with probability at least delta. You will
accept the probability at most delta.
No. The rejection probability is at least delta. The acceptance probability is at most 1 minus delta. That's what in this case. Let me add up all the rejection in this one. So you're going to
To upper bound
is 1 minus delta. Is that what? Yeah. Yes, yeah. So that's it. I'm going to keep bounding that. So then the test can pass only with probability 1 minus. Strictly smaller than 1, let's make it strictly smaller than 1 minus. Just this one. Therefore, this can't be the setting of the case, because you know the test is passing with probability greater than 1 minus. Let me make this. So this can't happen. To F this. So at this point, we'll assume that. So from now onward, we'll assume delta F. There exists a Z, so the delta F LZ is less than or equal to delta. You know it's close to linear from the for the next conditions also. Now F is delta far from being linear. This case, once again, if that was the case, that would have accepted. So here you can assume there exists a B such that delta. This point, you know that if you have gone through, if bad event 2 also had not happened, then you have this is less than or equal to delta. Then the next case is B is not equal to ZZ transpose. But this is the quadratic correlation test takes care. What's the maximum acceptance probability in this case?
3 by 4 plus
3 by 4 plus 3 by 4 plus 4 delta. So as long, so I would want to set it up such that this is less than or equal to 1 minus delta. I will choose my delta such that this happens. 4 is, so now we can assume B is equal to ZZ transpose. Now C of C is not equal to 1. Then this test will violate. And what is this one? That will be half plus 4 delta. Because you are querying 4 points. The points could have been the erroneous points. Yeah, so you choose delta to be small enough, this will happen. Therefore, one of the things will catch you, and that's the end. I think delta not being 1/20 works. I'm not sure. Basically, you need to check something. This is true or this is true. One of them will.
I think I got lost somewhere. So we are trying to show we are assuming that the verifier accepts the probability 1 minus delta.
Yes.
And from that, you want to conclude that conclude these things.
Yeah.
Etc.
Yeah. Okay. So suppose, let's do it with contradiction. Suppose such a Z does not exist. Huh?
So one of the 3 events, the 4 events should happen. Either F should be far from LZ, little f should be far from LZ, or capital F should be far from some word, something Z prime.
Yeah.
Or they should be inconsistent, or the circuit consistency check should have failed.
Yeah. So each of the cases we have said, if
Or the circuit or C of that is not
one.
These are
Not.
the 4 events.
Yeah. So those are the 4 events, but I'm going to assume that each one, this is the case, and then that happens in if F was delta far from being linear, the test would have accepted a probability at most 1 minus delta. This already violates the hypothesis.
Right.
So now you can assume F is delta close. Let that close be some C. Let's fix that. Now it could be that F is capital F is delta far. Once again, you have 1 minus delta. So now you have the proof has committed itself to a capital B at this point of time. That's a capital B, that's a capital Z. It could be that B is not equal to ZZ transpose, in which case you now reject with
That
probability.
would have been a rejection probability, but the rejection probability is actually less than delta. So we are accepting the probability 1 minus 2.
Yeah.
So we want
So
to,
this is the rejection probability. So yeah, so possibly I should have made this. What's the acceptance probability? It's 1/4 minus 4 delta or? Huh?
Yeah.
Yeah, so this should have been 1/4 minus 4 delta. Yeah, that's where the 1/20 comes from. Okay, so. No, what I want to say, what's the maximum acceptance probability? No, what I wrote there was previously correct, no?
yeah, so we would have accepted with probability at most 3/4 plus 4 delta.
Yes.
But we are accepting with probability 1 minus.
No. So the delta has been chosen. So assume the delta has been chosen small enough. So
That to be less than.
that to be less than this. Yes.
So that's not the case.
No, that is the case. So so delta has been chosen small enough such that this happens. So and that is exactly the word delta. If delta is smaller than 1/20, this happens. So
Exactly 1/20.
this is where the 1/20 comes. So here I have this. So now I can assume that B is actually equal to CZ transpose. And now come to CZ. So here the maximum probability of acceptance is half plus 1/4 delta. That is a random linear combination. Miraculously, you didn't pick the violating constraint.
Okay, and the 4 delta comes because we do this amount.
Because the points in query need not be the linear functions. It could be the places where they disagree. So half plus 4 delta. Once again, so these two are this is happening because delta is less than or equal to 1/20, and this is also delta is less. So each of these bad events actually cannot happen, is what I'm claiming. Therefore, you must have the and of these, which is what. Yeah. What is the? Probably not the best way to state it, but yeah, I don't see how cleaner way to do this. Anyway, what have you got at the end of it? Let's look at the PCP verifier. Something quite remarkable about this verifier. What's the number of queries?
10 something. 10, 15.
So it's 1, 2, 3. So there are possibly 6 queries in the first linearity test. Another 4 queries in the quadratic correlation thing. Technically speaking, it need not be 4 queries. There's actually just 1 extra query if you're going to reuse. We did just union bounds. So technically, it could be just 1 extra query. So 6, 7 queries. And 7. And it's just 2 more queries. So it's 9 queries. The whole object makes 9 queries, or if you want to add these, it's 14 queries possibly. So it's a 14. Number of queries is say some 9 or something. Then what's the number of randomness? So it's basically order n squared. And in the S case, you accept with probability 1. In the no case, you accept with probability at most 1 minus 1/20. Therefore, this is a proof of the fact that circuit SAT is in PCP 1 minus 1/20 order n squared 9. And the key thing over here is this 9. The n square is bad. The very fact that we are able to get some PCP verifier that queries the proof only at 9 is querying at 9 bits. And it's guaranteed with probability 19/20 that this is a correct proof. It's a fairly remarkable thing that is here. This is a humongous proof. It's an exponentially long proof. It's going to query it only at 9 bits. Yet it's guaranteed that this is if it passes, the underlying circuit is satisfied. It's quite a remarkable statement, and of course, it doesn't give you the PCP theorem because the randomness is n square. Despite that, this is quite. And we will, by the way, we will need this for the eventual proof of the PCP theorem. This will be an essential ingredient.
So we couldn't do this directly for 3 sets because we will get 2 big polynomials.
Huh? Yeah, I didn't do it directly for 3 set because I would get, but I think even 3 set you can sort of express it as
It's a circuit sentence.
it's a circuit set instance, so you just make it into
Again, convert.
yeah. So the point is, once you linear is not is a problem in P. Once you get in quadratic constraints, you can capture all of any constraints. Therefore, that's all that we needed. Okay. Any questions? Now, again, the point that Nadal made is something we'll use. So we're going to use it eventually in the proof of the PCP theorem. This PCP theorem, note the statement here. What I wanted to show the soundness was only that there exists a reason that CZ equals 1. But we not only show that CZ equals 1, that the proof there contains within it, its belly, this satisfying assignment. And this is a part we will use the stronger property, the way I stated it now, when using this PCP, using this constant query PCP to complete the proof of the PCP here in the next few lectures. Okay. So where are we going to go from now? From now onwards, what did we show? If we had a locally testable code, which was constant query testable, we knew how to use that to construct a PCP. And Hadamard code was one such. The Hadamard code was one such code. The nice thing about this code was it constant query testable. That's why we were able to get, it was 3, that 3 became 9 or 14 or whatever out here. The bad thing about that code was the fact that the rate is this one. So if you could design another constant query code, testable code, then which had better rate, one could conceive doing this. So that will be our next goal. Is there another? Unfortunately, we won't be able to get a constant query code which has better rate. What we will show is that the Reed-Muller code is a locally testable code, but not necessarily with constant queries, but with some amount of queries, with polylog queries. So what we will do is, but it will have rate to be inverse polynomial and not inverse exponential. So we'll first show that the Reed-Muller code is locally testable. This will be the low degree testing. It will be the counterpart for the linearity testing. We'll show the Reed-Muller code is locally testable. Then we will show that Reed-Muller code is powerful enough. You can do all this quadratic, the circuit consistency test. So we'll construct a PCP based on the Reed-Muller code, which will have polynomial blow, not so the proof length will not be 2 to the n square, it will be polynomial, but the queries will be polylog n. It won't be constant. We'll have both of these objects. We have a constant query PCP with exponential rate, and then we have a polylog query PCP with polynomial rate. We'll somehow see how to put this. This situation is very similar to coding in code concatenation, where you had a code which you had Hadamard codes which are very good with extremely good distance, but inverse exponential rate. The Reed-Solomon code which has very good distance, but over a large vessel. You do code concatenation to put them together to get a final good code. We'll do the same object here. We'll do the corresponding version of code concatenation, which will be proof composition, to put these both together and do. So the next few lectures will be going into low degree testing, Reed-Muller testing, and then building a PCP out of it. And then we compose these PCPs to finally finish the proof of the PCP.
So, instead of Hadamard code, if you use matching vector codes, we will get abstract queries.
Matching vector codes are locally decodable, they are not locally testable.
Locally decodable is already because when you recover
no. Locally decodable codes tell you if you are close to the code word, I will know. But you need to first check that what is given is close to the code word. So here you are requiring both local testability and local decodability of the code.
Because that's not, I mean, that's not all, right? The way the proof was sort of formatted here, the semantics were very intimately connected to the fact that we are going to look at Hadamard code. we can't just, if we replace hard code by some other locality.
It's not clear.
You have the relation.
No. Right now, it's all very tailor-made in this one. That's why we don't get. For example, last year's talk with the stock bus paper one, a constant query, constant rate LTC was constructed. That immediately didn't give a PCP with constant rate. And this one, because this is transformation is not black box. It's very specific. One. Yeah. Kehan, you had a question?
No, I was just listening to the discussion, but thanks for the lecture anyway.
Okay. Anything else?
So the properties of element code we needed here was local testability and local reproducibility.
So the problem with these proofs is I don't know how to abstract it. These are the properties of the code that I have, and from that I can do it. So it would be nice to do this. There have been this ones, but there seems to be more about them than more about these codes that I use than just I can't get this property, and if I have this property, I can do it. Yeah. Okay, I'll stop with this.